Okay, ready for the next one? Here we go. The concentration of a drug in the body decreases exponentially after a dose is given. Okay, so right away in that first sentence, it's telling me that it decreases exponentially, which means we're dealing with what kind of model? An exponential decay model. Okay, so we know the formula for that, so let's just keep going and see what else it tells us. In one clinical study, adult subjects averaged 13 micrograms per milliliter of the drug in their blood plasma 1 hour after a 1,000 milligram dosage, and 5 micrograms per milliliter 7 hours after the dosage. Okay, so you're like, okay, I get there's a lot going on there, but here's what I do know. I do know that they had 1,000 milligram dosage, right? And let's see. After 1 hour, we had 13 micrograms per milliliter left. And after 7 hours, they had 5 micrograms per milliliter left. Correct? Okay, gotcha. Now, part A says find K. They want you to write an equation for the exponential function that can be used to predict the concentration of the drug in micrograms per milliliter T hours after this 1,000 milligram dosage. Okay, so part A, they basically want us to find the equation, right? The exponential function. So, me, I like using my variable P. If you're okay with that, I love it. I appreciate it. All right. So, I do know after 1 hour that 13 micrograms per milliliter is left, don't I? Okay, and then after 7 hours, 5 micrograms per milliliter is left, correct? Question. I know I need to find K because I said it. Do I know the initial amount? Be careful, because some of you said yes. Some of you are going, okay, because you asked me that question, I'm not sure. Yeah, I purposely asked you that question to make certain you're thinking. I know the ending amount is either 13 or 5, whatever I want to use, but look at the units. It's micrograms per milliliter. If some of you were thinking the initial dosage is 1,000 milligrams, that would be incorrect. Why? Because I'm not going to have an initial dose of 1,000 milligrams and end up with the unit microgram per milliliter. It doesn't jive. With me? If I input milligrams, then I should come out with milligrams, not micrograms per milliliter. So the initial dosage is not the 1,000 milligrams as you would assume. So just watch for a second. Bear with me. Hear what I'm saying. All right. I do know that the ending is 13 micrograms per milliliter. I don't know the initial amount. I know that it's after 1 day. I basically have two variables here. I have P sub 0 and K in this equation. I know I need to solve for K, and I need P sub 0. So here's the deal. Algebraically, two unknowns means I need two equations. So I need a second equation here. And my second equation is going to be the second piece of information. I know that I have 5 micrograms per milliliter left after 7 hours. Cool? Okay, so now I have two equations and two unknowns. Got it? Now, I'm going to do something very simple to help me eliminate one of the variables. Because to be honest with you, when you have two equations and two unknowns, you can either do a substitution technique or you can use an elimination technique. I'm going to use an elimination technique because the elimination technique is going to be actually very simple. How am I going to eliminate? I'm going to eliminate like this. I am going to take my two equations and I am going to divide them. And they're like, why are you dividing? Because if I take them and divide, I am going to get rid of the piece of zeros. I'm going to be left with 13 over 5 on this side equals E. Now here's something you need to remember. And I'm going to sidetrack you for a second. What happens if you have x to the second over x to the fifth? What would that be equal to if you simplify that? Yeah, x to the -3, right? Because you would do 2 minus 5. Rules of exponents, yes? So I have e to the 1k over e to the 7k. What would you get? E to the -6k, right? Because when you divide, you subtract the exponents. Let me rephrase. When you divide the same bases, you subtract the exponents. I divide the bases of e, I get to subtract those exponents. Good? Okay. You're like, yeah, but the elimination technique is usually addition or subtraction. That's true. But depending upon the actual equations that we're working with, sometimes you get to divide. And that helps to eliminate also. Because eliminate means get rid of. And I did. I got rid of piece of 0. So I was left with the k, which is what I'm actually trying to find anyway. With me? Okay. So now I am going to take it over here. I have to natural log both sides, as you well know. And then I get to divide by that -6. And your calculators are out. I know it. And let's see. Round to 3 decimal places, please. Why? Because it asks us to. So, what did you guys get? Okay, good. Sounds like we got the same thing. -1.9 is approximately k. And I say approximately because we rounded. Got it so far? Okay, so here's the deal. Our function right now is looking like P of t is equal to P sub 0 e to the -0.159t. And gratefully the k is negative because it did tell me it was an exponentially decreasing model, right? Okay. Found the k. This is what it looks like so far. Now, here's the deal. I actually am going to need the P sub 0. Because you notice in part A it says find k and write an equation that can predict the concentration of the drug. Well, I found k and I've got an equation, but it's not quite finished yet. Because remember, you need P sub 0 to actually make this equation complete, this function complete. And you're like, well, how are you going to find P sub 0? Don't I know that after 1 hour, 13 micrograms per milligram is left? Or after 7 hours, 5 micrograms per milligram is left? If I knew T and the ending, couldn't I find the initial? Yes, I could. Which means I could actually take one of these two pieces of information, plug it into here, and find my P sub 0. So, which one am I going to use? I'm just going to use the first one. I'm going to use the fact that we had 13 micrograms per milligrams left. P sub 0 e to the -0.159 times 1. Right? Because time was 1 hour. Agreed? All right. So back to our algebraic stuff. I need P sub 0 by itself, so it looks like I have to divide by the e portion, don't I? And gratefully anything times 1 is itself, so I don't have to worry about the 1, which is another reason I chose the 1 hour and 13 microgram per milliliter. Got it? Okay. And so I end up with P is approximately, what'd you guys get? Yeah, I got approximately 15 micrograms per milliliter, which means your actual function, your specific function for this particular problem is P of t equals 15 times e to the negative 0.159 t. There is my specific equation. Part A said find k, we did, but it also said find the exponential function, which means I now needed to find p sub 0. And there it is. And there is my, I should put a sub 0 here, I'm so sorry. And there is my actual equation, my actual function. Good? Okay. So, now that we got that, let's go to part B. Part B says estimate the dose, or pardon me, estimate the concentration of the drug 2 hours after the dosage, after the 1,000 milligram dosage. We're still talking about that 1,000 milligram dosage, which is very good, because if they threw another dosage at me, I'm going to have to start all over again. It's very important that they stay with the same dosage. Okay, so 2 hours, right? So the amount after 2 hours. Okay, I know, get those calculators out, because all it is plugging in that 2 for time, isn't it? And gratefully it's in hours, right? Because these units are all in hours for time. Okay. What'd you get? Yeah, mine was approximately 11 micrograms per milliliter. Good? Okay. Now, finally, part C. Part C is asking to relieve a fever. The concentration of the drug should go no lower than 5 milligrams per milliliter. After how many hours will the 1,000 milligram dosage drop to that level? Okay, so some of you are like, wait, don't we already have the answer? I agree. But they're not always this nice on part C. But let's still make sure you understand how to figure it out. They say the concentration of the drug should go no lower than 5 micrograms per milliliter, which means this would represent what in our equation? It's the ending amount, because they asked you how long is it going to take, after how many hours, which means you're searching for the time. All right, so we're plugging it in. We are going to do our algebraic steps. I'm dividing both sides by 15, which is why I get 1/3. Don't put it as 0.333 because it's a repeating decimal. Leave it as 1/3. You don't want a decimal in there that's repeating, because you will have a tendency to round it, just like I would, and then I'm going to throw off my answer. Natural log on both sides. And yes, I'm taking the natural log of this fraction and divide both sides by that negative decimal. And now that I have this, I'll punch it into my calculator, and I'm going to round to the nearest day. Pardon me, I'm going to round to the nearest hour, because the time is in hours. What'd you get? Good, approximately 7 hours. Which is what I know we should have gotten, right? But this proves that I get the 7 hours. So we did everything correctly. Gratefully, we found the correct K, we found the correct P sub 0, we did everything right. Part C actually shows it for us, even though they wouldn't give you 5 milligrams in most of these problems. They probably would have said 3 milligrams or whatever. Not milligrams. Microgram per milliliter. They wouldn't have given you 5. They may have given you 3. They may have given you 4. I don't know. Whatever floated their boat. Cool? Okay. Stay tuned. Got another one. Okay, let's look at this next one. The annual consumption of beef per person was about 65.5 pounds in the year 2000. and 61.4 pounds in the year 2007. Assume B of T represents the annual beef consumption T years after 2000. So I'm going to stop for a second because there's a comma, so that means pause anyway. So B of T is the annual consumption T years after 2000. So 2000 represents what? Yeah, time is 0. So this is time equals 0, isn't it? All right. After the comma, assume that it's decreasing according to the exponential decay model. Okay, that's right. Write the exponential decay model, right? Oh, by the way, it said B of T, not P, so let me put the B in there, right? B sub 0, e to the kt. So we have an exponential model, and it's an exponential decay model. They were very plain about that, so there it is. Okay, part A wants you to find k and then give them the equation. All right, so here's the deal. What do we know? Yeah, we actually know that in year 2000, t is 0. So what does the 65.5 represent? It represents the initial amount. Excellent. So I know the initial amount is 65.5 at time is 0. What I don't know is the k. So if I'm looking for the rate, because that's the other piece of the puzzle I need to write a specific function, if I'm looking for the rate, that must mean I need to know t and I need to know the ending. Do I? You're right, I do. I do know at t being equal to 7, my ending is 61.4, don't I? So to find the k, my ending balance is 61.4 equals 65.5 e to the 7k. Are you with me on that? Yeah. As soon as I knew t equaled 0 was the year 2000, then I knew the initial amount was 65.5 pounds. And gratefully, in order to find k, gratefully they gave me another time and an ending balance so I could plug it in and go find k. Alright, so maybe you should pause the video, solve for k, and then come back and let's see if we agree. I am going to do my algebraic work. Oh yeah, this is part A. I should have written that down. And I'm going to take the natural log of both sides. And I'm going to divide by 7 on both sides. Boop. So let's see. What did I get for k? I got k was approximately, and we're going to round to 4 decimal places because that's what it wants us to do. I got k was approximately negative 0.0092. Did you get the same? Awesome. Okay. And now there's a part B. Oh, wait. Yeah, wait. I got the k. Maybe I should actually write the specific equation. Yeah. Can't go to part B until I got my equation written down. Okay, so here's your specific function, I should say. Excuse me, function, because it's a function, not an equation. So B of t is equal to 65.5 times e to the negative 0.0092 t. Got it. All right. Now I can go to part B, right? Okay. Find the consumption, or estimate the consumption of beef in the year 2014. What does it want? The ending balance, which means you need to know the time. They told me the year was 2014, so what's your time? Good, 14, right? Because that's 14 years after 2000. All right, so the beef consumption after 14 years. Always good to write this down. I know some of you went straight to your calculators, but trust me, it's always good to write this down to make sure that you finger punch correctly. And please round to the nearest 10th. Got your answer? All right, you guys have quick fingers over there punching on that calculator. I got 57.6 pounds. Good. So far, so good? Loving it. And then there's a part C. In what year, theoretically, will the consumption of beef be 10 pounds? All right. So how do I find part C? Yeah, they said what year, so what are we looking for? Yeah, you're looking for time now. And what's the 10 pounds? That's the ending. So that means you've got 10 equals, correct? All right, 65.5 e to the negative 0.0092t. Okay, we've come up against these equations before where we're solving for an exponent. Have at it. Let's see if we agree. Let's see if you follow my steps. Whoops, equals. You know, the nice thing about these is the functions are basically the same type of function, right? So when you know how to solve one of them, you basically know how to solve all of them. So I know it's repetitive, but it hones your skills. It sharpens your skills. Yep. I ran out of board space. So, round to the nearest whole number, please. What did you get? Yeah, I did too. You're like, is that right? Well, they did say theoretically. 204. 204 what? Yeah, T is in years, so that's 204 years. Now, wait a minute. 204 years after the year 2000, right? After 2000, which means theoretically, because they said in what year theoretically, 10 pounds of beef consumed per person is going to happen in the year 2204. That's theoretical, all right. As of this making, this is the year, what, 2021? Got a few more years to go. Stay tuned. I got one last problem. Okay, ready for this last one? This one's kind of one of my favorites. Why? Because it's an everyday real life problem. Now mind you, this is all programmed into computers. All of these examples are programmed into computers. But somebody's actually has to do the programming. They got to come up with the specific equation, the specific functions. With me? But as I said, this one's kind of a cool little example. So let's read it. A coroner arrives at a murder scene at 7 p.m. She finds the temperature of the body to be 84.5 degrees. She waits an hour, takes the temperature again, and finds it to be 82.1 degrees Fahrenheit. By the way, they're both in Fahrenheit, right? Okay, so that's a good thing. She notes that the room temperature is 71 degrees Fahrenheit. Assuming that the temperature of the body was 98.6 degrees Fahrenheit when the murder occurred, when did the murder occur? When was it committed? Okay. Not that, we want to come upon a murder scene or whatever, unless this is the field of study you're going into, then this problem is really going to be very apropos for you. But it's kind of a neat little problem because the body is cooling, right? But it's not a decay model. It's a cooling model. It's like if you took a pizza out of the oven and you're letting it cool, you're like, well, how long is it going to cool to the temperature I can eat it, right? It's as if you had a hot tub going on, right? You turn the hot tub off. How long does it take for the hot tub to cool down to a certain temperature? Anytime something is cooling down, it's a cooling model, not a decay model, which means we have to know Newton's law of cooling. Now, here's the formula for it, and here's what each of our variables represent. So my suggestion is to pause the video, write those down, and then start up again. Okay, got it written down? Then here we go. So let's see what pieces of information they've given me. So I'm going to start back at the beginning. We got the murder, the coroner arrives at the scene at 7 p.m. Fine. So she arrived at 7. The temperature of the body is 84.5 degrees Fahrenheit. So I'm noticing capital T says the current temperature of the cooling object. So in this particular problem, the current temperature of the body, when she found it, was 84.5 degrees Fahrenheit. Got it. She waits an hour and then takes the temperature again and finds it to be 82.1 degrees Fahrenheit. Okay, so let's see. I don't really kind of see where that fits in, but it is a good piece of information. After 1 hour, the body temperature went to 82.1 degrees Fahrenheit. By the way, it's good that these units are all in Fahrenheit, because if they took one in Fahrenheit and one in Celsius, we'd have to convert it. So gratefully, they're using all the same temperature. She notes that the room temperature is 71 degrees Fahrenheit. Yeah, that's the surrounding air temperature, right? So they gave me C was 71 degrees Fahrenheit. So they gave me C and they gave me capital T. I'm noticing A. A is the difference between capital T and C, right? So they actually gave me A, and I can find A by taking the difference. Obviously, I need to subtract in the correct order, correct? And I notice that A is equal to 13.5. Do you agree with that? Okay. So, let's see what this is looking like so far. Capital T of little t is equal to A, which is 13.5, times e to the negative kt, plus C, which is 71 degrees. That's the surrounding temperature, correct? Okay, so as with any cooling model, right? It's not a decay model, but I'm going to kind of throw decay model in there because decay model means it's going down, it's decreasing, and cooling means it's decreasing. Besides knowing the initial amount, so to speak, in those decay models, what was the other piece of information we needed to know? We needed to know the rate. In this problem, K also represents the rate. Do I have the rate? No, I don't. If I'm trying to find K, here's the question. Do I know a time and the temperature at that time? I do. This piece of information that I wrote down but did not use yet said after 1 hour, the temperature of the body was 82.1 degrees. Since I know that, couldn't I plug it in here to find K? Good. So tell me what this is going to look like when you plug it in. Yeah, I heard you. You're going to write 82.1 equals 13.5 times e to the negative, 1k plus 71. Correct? Okay. So I now know my little t is in hours, don't I? Because they said after 1 hour. So I now know little t is in 1 hour. All right, so time to solve for k. What are you going to do first? Minus the 71 over. So what is that? 11.1 equals 13.5 e to the negative k. Boy, this line looks familiar, doesn't it? Okay, you know how to solve for k, don't you? Good. So we are going to divide both sides by the 13.5 and then take the natural log of both sides and then, divide both sides by a -1, right? Okay, so I'm going to put that over here. Round k to 6 decimal places. What'd you guys get when you rounded to 6 decimal places? Okay, I think I heard the same thing I got. K is approximately 0.19575. Good. You're like, wait, it's not negative. It's supposed to be cooling. So Newton's law of cooling includes the negative by the K already. So now when we go back and we write the specific function, it is going to look like capital T of little t is equal to 13.5 e to the negative, right? And then there's your K. 0.195745 t, and then plus that 71. Good? Okay. Now I finally have the specific function. Now mind you, they still want to know when the murder occurred. All right, so what am I looking for if I want to know when the murder occurred? I'm looking for T, which means I better know this temperature at that time T, right? Okay, now think about it. A person's alive, and then they get murdered. So at the time of the murder, what was the body temperature? Yeah, unless they were sick, right? The body temperature is the normal body temperature of 98.6 degrees Fahrenheit. By the way, they were very nice. They gave that to you. That's something you should know. It's kind of one of those common knowledge things you learned somewhere in a biology class, hopefully. So the body temperature was 98.6 degrees. That was actually the ending temperature, shall I say, right? Or the temperature at the murder, because after that it started cooling. And I'm trying to figure out what the time was that it started cooling down from here, because from here is where they were still alive, right? Okay. So we plug it in to the ending, and now we get to solve for that T. So what are we going to do? Minus the 71. So what do we get? 27.6 equals this 13.5 e to the lovely decimal up here for rate. Divide by 13.5. Yep, this process is looking very familiar. And then what would you do? Yep, you're going to have to take the natural log. And I'm going to bring that up over here. Hopefully I've got enough room. Natural log of 27.6 over this 13.5. And then I'm going to have to divide it by that decimal, right? Yeah, I'm sorry, I skipped a step. Why? Because I'm running out of board space, but I'm sure you wrote it down. Equals the T, right? Okay, so calculator, plug it on in. Tell me what you got. Okay, I believe I heard you say a negative 3.6, right? Time is in hours, so that's a negative 3.6 hours. They want me to round to the nearest hour. Well, since it's negative 3.6, that would be a negative 4 hours, which tells me the murder happened 4 hours ago, because the negative is telling me it happened in the past. So it happened 4 hours ago. So if the murder scene, the coroner arrives at 7 p.m., and 4 hours ago, according to her estimation or his estimation, the murder happened 4 hours ago, that means that the murder occurred at 3, what, p.m. or a.m.? p.m., because it was only 4 hours, right? Didn't get into a.m.s. Make sense? Yeah, this one's kind of a cool little problem. Newton's law of cooling is a neat little decrease model still, but it's a cooling model versus a decay model. You only use Newton's law of cooling when you're trying to cool things down, like a pizza out of the oven, or water from the hot tub, or unfortunately a body from a murder scene, right? Those type of things. They're cooling, they're not decaying. Good? problem for this section. I hope you got the gist of what was happening here. Have fun with this section, and I'll catch you on the flip side.